symmetry.
Okay, thank you very much. It's a pleasure to be here. I'm going to inject a dose of Fukaya categories into this very algebraic conference. So I feel like a bit of an outsider, and as a result, maybe I will try to give more a general picture of a theme rather than very specific cutting-edge results. I mean, if I can get people a bit interested in Fukaya categories and homological mirror symmetry, that's maybe more of a goal. Okay, so what are Fukaya categories? Well, one way to sell them to a non-commutative audience is to say they're a useful source of potentially non-commutative Calabi-Yaus coming out of symplectic geometry. And I'm going to try to give this talk so that you don't need to know anything symplectic. It's just a word, basically. Maybe not quite. But so the starting point is if I have a symplectic, a real symplectic, I don't have any holomorphic symplectic geometry. So it's a real manifold of even dimension. You can think of just a Kähler manifold. That's good enough for us today. Then there's a construction which associates to it an infinity category called the Fukaya category, or closer for us, the wrapped Fukaya category, when Y is non-compact. This is going to be pretty much always a Calabi-Yau infinity category. It's only Z mod 2 graded in general. It will be Z graded only if Y itself is Calabi-Yau. There's a lot of funny things like that happening, that the terminology for whether a category is Calabi-Yau, smooth, and so on comes from the intuition of derived categories in algebraic geometry. And those properties under mirror symmetry translate to different properties of symplectic manifolds. So this manifold being Calabi-Yau as a manifold translates to this being Z-graded. The category itself is always Calabi-Yau. It's often smooth. I will not say what I mean by often. And it's proper if Y is compact. And then what else do you want to know? So the objects of these categories are things called Lagrangian submanifolds, which are half-dimensional submanifolds in your symplectic manifold. So they have real dimension n inside something of complex dimension n. And morphisms try to detect intersections between these Lagrangians in a way that's robust under suitable isotopies called Hamiltonian isotopies. Okay, so main things you want to know are that the objects are things called Lagrangian submanifolds. And morphisms correspond to, well, I mean, they're really vector spaces over some ground field spanned by, I would say, intersections or perturbed intersections of Lagrangians. Okay, so, but I don't like this restriction to only look at Calabi-Yaus. Kontsevich in 1994 reformulated mirror symmetry conjectures by saying the existence of a mirror symmetry phenomenon between a pair of, say, projective Calabi-Yaus manifests itself in the statement that if I have, so I have a mirror pair of Calabi-Yaus, which at the time was basically motivated by physics, or was a phenomenon acknowledged, but it wasn't really understood yet how to build systematically such mirror pairs outside of toric settings. Then there should be an equivalence between the derived category of coherent sheaves of X and the Fukaya category of Y, and vice versa. Subsequently, it was found that we don't really need to restrict ourselves to Calabi-Yaus, but that means we need to enlarge the field of possibilities to get rid of this property that this category is always Calabi-Yau, obviously. So this is achieved by considering the geometry not just of a symplectic manifold, but what's called a Landau-Ginzburg model, which is a manifold with a complex valued function. The role of that function is that you will look not just at the geometry of your manifold, but your manifold relative to, say, the regular fiber of that function. Another way of saying it is that you're probing the singularity theory of that function. So this extends beyond Calabi-Yaus if we allow ourselves to consider something called Landau-Ginzburg models. That terminology comes from physics. You don't need to know any physics for this. What is Landau-Ginzburg model for us? It is simply a manifold. For the symplectic geometry side, a symplectic one. For the algebraic geometry side, some quasi-projective variety or something like that, together with a map to, well, basically a regular function on it. Okay. And so what we're supposed to do is associate to this a Fukaya category of the pair consisting of the space and the function on it, which is supposed to look at the geometry of, so I think the best way to say it is y relative to the subset, we'll call that y infinity, which is the set of points where the real part of W is very negative. There's a convention here going on. And by some trickery, like about excision and so on, or whatever, this reduces to really understanding the critical locus of W. Okay. So rather than trying to give a complete definition, let me give you an example of what kinds of things we want to do with that. So let's say that we are interested in C star squared. Okay, that's a, well, that's whatever it is as a symplectic manifold. But let's say we look at the function Z1 plus Z2 plus 1 over Z1 Z2 on that. So, okay, you can start calculating things and seeing what happens. What happens is the generic fiber of this is a 3 times punctured elliptic curve. So I will draw that as something like this. And moreover, this has 3 isolated non-degenerate critical points. Which are like basically at 1,1 times a root of unity. So in fact, there's 3 critical values. And the fibers above those are nodal degenerations. So I'm going to try to draw something like this. So this is not, anyway. So there's 3 of those, which are nodal degenerations of the regular fibers. And so if you want to understand, say, for example, the relative cohomology of C star squared relative to, so I guess this minus, y infinity lives over here, then you see that basically the core of the topology is going to come from the fact that if not for these 3 singularities, things would retract away and you'd get something trivial. And so the interesting part of the topology really comes from some specific cycles. Sorry, wait, well, I still mean relative to that in the sense that you avoid that. And so I have some Poincaré duality going on in my head that, anyway, so the claim is the interesting kinds of Lagrangian submanifolds to consider in this Landau-Ginzburg model are half-dimensional, so real 2-dimensional submanifolds, which go to infinity when you project them only to east infinity, because west infinity is forbidden. And up to wiggling and deformations and so on, the most interesting ones there are, in fact, well, the ascending submanifolds of the Morse critical points of the real part of W. Right, so these are ascending manifolds of, well, the Morse function, a real part of W, are Lagrangians. And these are called Lagrangian thimbles. Terminology goes back, I think, to Seidel, possibly even before. Okay, so you can do this at each of these three things, and you can ask, well, okay, what am I getting myself into? Why am I doing all this? If you're really motivated, you can say, well, because I can try to calculate a Fukaya category with this. Okay, so how do we calculate a Fukaya category with this? So we're supposed to try to intersect these Lagrangians with each other. And at first glance, it's easy, they don't intersect. But that's not what we're trying to do. There's another bit of the rules that are going to come up, which is that when we perturb things, and this is, there's going to be an asymmetric perturbation, which is going to break the fact that if you have two submanifolds A and B, A intersection B, B intersection A are the same thing. And roughly speaking, that's why honest Fukaya categories tend to be Calabi-Yau. Okay, so we're going to break that by saying that when we define hom of AB, this is going to be generated by intersections between some perturbed copy of A with B, for example, where, so this is like a flow which pushes infinity in the positive direction. So you might ask, what is the positive direction? Well, here I will answer concretely. You have a copy of a complex plane. You know what is the positive direction in the complex plane. In the fibers, you have a punctured Riemann surface with cylinder ends. You know what it means to go positive direction along the ends of your Riemann surface. Symplectic geometry tells you how to have a generalization of this in higher dimensions, but I don't want to say it now. So the flow pushes at infinity in the positive direction without crossing into the forbidden zone, which is sometimes called the stop. And the fact that we are putting a stop here at left infinity is what causes this category to not be Calabi-Yau anymore. So concretely here, we have three objects, which I will call L-1, L0, L1. And you might ask, okay, what morphisms do we have between them? And the observation is that this actually is going to give you something that's directed, because if I push L0 up, well, it's going to be even more disjoint from L-1. So there's no morphisms from L0 to L-1. On the other hand, from L0 to L1, well, after I've pushed L0 up, it will intersect in the fiber above this point. So now I need to understand the vanishing cycles of these two critical points, how many times they intersect. And the answer is they intersect in 3 points. It's like a calculation with pictures and so on. Okay, so there's 3 morphisms here. For the same reason, there's 3 morphisms here. And from L-1 to L1, there's something of dimension 6, which is best described as, well, these two are in fact isomorphic vector spaces under rotating the whole picture. And this is like sim2 of that vector space. And what you have here is the beginning of describing the derived category of P2 and its exceptional collection, O of -1, O and O of 1 in dB of P2. These form an exceptional collection. There's 3 sections of O of 1 and 6 sections of O of 2, and that gives me the same picture. So what I've done here is I've botched an attempt at explaining what homological mirror symmetry for P2 looks like. The mirror of P2, well, one of the mirrors of P2 is this Landau-Ginzburg model. Its Fukaya category, well, there's other Lagrangians I could consider, but the claim is it's generated by these 3. And these 3 form an exceptional collection, which matches with one of our favorite exceptional collections on P2. Okay. All right. well, there's a calculation to be done inside. So, right, so there's a fiber over this pink point. And in there, I'm supposed to look at the two vanishing cycles. And the claim is one of them will look kind of like that. And the other one will look like it twists 3 times around. So it's very hard to draw, but it's a calculation, okay, to check how many times the vanishing cycles of these two nodal degenerations meet. There's other ways to calculate that, but that would get us. I mean, back when this was new, Seidel gave like a semester-long class on basically this example, but okay. All right. Okay, so there's calculations involved. And certainly also, I think that's not obvious is when you try to calculate products, compositions in Fukaya categories are very hard to calculate directly because they're given by counts of holomorphic disks. So what you're supposed to do is go out and take out your complex analysis toolkit and start looking for holomorphic maps from a disk to C star squared with boundary on your given Lagrangians. In practice, you can do that here because you have like a holomorphic projection down here. So you look for triangles in the base, and then within the fibers, you again do that. So there's a dimensional reduction that kind of saves you here. But in general, this can get extremely nasty. All right. So, well, that is great. But now I'm going to throw a wrench into this because, I mean, most of that story is like, I would say around 20 years ago. This was new and exciting. I feel like something I need to tell you, which will make it slightly more new and more exciting, which is that, so now we should think of a Landau-Ginzburg model as a locally trivial family of symplectic manifolds. Oh, sorry, yes. So these are generators of, these are an exceptional collection of 3 specific objects that generate the Fukaya category. Okay, so yes, so the Fukaya category of C star squared W has an exceptional collection consisting of these 3. It's a full, strong exceptional collection generating it and so on. And this is equivalent to dB of P2, which has, okay, all right. And so that's the kind of statements that you would like to get to, except if I move away from simple things like projective spaces or Fanos or and so on, I'm unlikely to have some orthogonal decompositions in this kind. So my favorite examples will not have this like gentle story where you can nicely split things into simple singularities. Okay, we should imagine that we'll want to have really nasty singularities instead. Okay. So the next thing I wanted to say, I forgot to say, so all the smooth fibers, this may be surprising to algebraic geometers among you, but all the smooth fibers F are actually symplectomorphic. We have the same symplectic manifold. This is like one of the nice things about symplectic geometry, that if you deform a symplectic manifold, keeping the cohomology class of the symplectic form constant, you've done nothing. So all the smooth fibers are isomorphic. And you could try to say, well, these kinds of Lagrangians that project to arcs, they are in fact obtained by looking at a Lagrangian in the fiber and moving it over an arc. And that's basically exactly what's happening. Okay, so of special interest are fibered Lagrangians in Y. This is L in Y, whose projection under this projection is some arc or something like that. And over each point of this arc, maybe each generic point of this arc, this is going to be intersecting each fiber over gamma in a Lagrangian, let's call that little l, which will be an object of a Fukaya category of a fiber. And so now we see something interesting happen, which is that we might hope to be able to go back and forth between the Fukaya category of a fiber, that of a total space y, and that of a pair y, comma w, the function. And that's basically the theme of the talk is what are these functors and what do they mean in this dictionary of mirror symmetry? Okay. So these ones you could say are strictly fibered. More generally, you could look at Lagrangians whose image consists of a blob, but at infinity, they might be fibered over one or more arcs. And that would be also okay. And in fact, it's kind of a postulate in some of the definitions of this Fukaya category that you only want to allow Lagrangians with this kind of technical condition. So I would say there's almost as many different constructions of a Fukaya category of a Lenox-Ginsburg model as there are papers on the subject. Certainly there are more than there are authors on the subject. And they differ in how do you make it well-defined to calculate intersections and perturbed holomorphic disks and so on. When you do complex analysis in a non-compact manifold, you need to know that holomorphic curves will not escape at infinity. My favorite way to do that is we have been kindly provided with a holomorphic projection map to the complex plane. We might as well make sure that everybody stays fibered over arcs, because then we can use the open mapping principle and say, hey, everything has to live over polygonal regions in the base. And then once you've done that, you can worry about what happens inside the fiber. So anyway, so I'm going to like these kinds of Lagrangians. And so to be slightly more precise, the objects are going to be Lagrangians in Y, which over the complement of, let's say, compact subset of C. So let's say, let me simplify this, such that, let's say, where W is bigger than, I don't know, let's make it 1, for example, but this is an arbitrary constant, is a union of embedded arcs in C, avoiding the direction of minus infinity, okay, the forbidden region. And so, this is an attempt at drawing things like that. So when we have such a category, then we can hope to have essentially this way of choosing the setup. Sorry, so morphisms will be intersections after perturbing. So how do we perturb? Well, in the base direction, move the arcs counterclockwise inside the complex plane without going to minus infinity. Okay, so you want to push your arcs so that the ends of all the ends of one Lagrangian lie counterclockwise from all the ends of the other. That's when you know that you've pushed enough. But you don't want to cross left infinity. And in the fiber, there's also a positive perturbation. Okay. As in wrapped Floer theory or whatever Fukaya category we have for the fiber itself. So when we have this, we get for free a pair of functors between this Fukaya category and the Fukaya category of a fiber. And those are the key protagonists of this talk. So which way do I want to write those? Okay. So there's a pair of functors denoted by cup and cap between the Fukaya category of a fiber and that of a total space with this function. So what is cup? Well, this is transport a Lagrangian inside the fiber over a U-shaped arc that goes around all the critical values. So you have the critical values of your map W, and you just take an arc shaped like this. And so I just want to make sure I have the correct notation. Otherwise, all my adjunctions will be backwards later. Yes. So you start with putting L in this fiber, and you use the fact that all of those fibers are isomorphic when you follow around to follow this Lagrangian, and it comes back, well, not quite as the same Lagrangian, because there's a monodromy around all these singularities. Right? The monodromy of W around all the critical values is something I will call mu, which is monodromy of the fibration around the critical values. And this is a symplectomorphism of F. So it's a functor, in fact, an autoequivalence of the Fukaya category of the fiber. Okay. All right. So by this picture, cup of L is a Lagrangian in Y whose projection is this kind of U-shaped arc, and which in each fiber over this arc looks like a copy of little L, except by the time I've gone back all around, monodromy has done its work. And for reasons that, well, one has to choose a convention somewhere, I'm calling mu the monodromy in the positive direction around. And so this is the inverse monodromy because I'm going clockwise around. There's, of course, a version of this where instead you put L here and you get mu of L over here, but then the adjunctions I will have in a moment will be reversed. Okay. So what is the other one? So cap. So okay, so this one is called cup, like because the symbol has a shape of a U, and you go over a U-shaped arc, so that's convenient. Cap is supposed to make you think of intersection, and that's convenient because it's indeed intersecting with the fiber. So more precisely, this is something that goes from category of YW to actually a slight enlargement. I mean, maybe it was already built in there. So this is like so-called twisted complexes. This is just a triangulated enlargement where you add mapping cones to the Fukaya category. Mapping cones of morphisms in the Fukaya category, sometimes you can interpret as taking two Lagrangian submanifolds and sticking them together and deforming a bit. And sometimes we have no idea what to do geometrically, so it's safer to stick it here. So what this does is takes a Lagrangian L and maps it to, so let's say our Lagrangian L projects to some kind of blob, but with some ends, okay? Then you look at all of the fibered ends. Inside, over each fibered end, you have a Lagrangian submanifold of a fiber. So what you do is you build a twisted complex built out of the ends of L. And then there's a differential in this complex. And the differential in the complex is given by counting holomorphic sections of the fibration with boundary on L. So there's a differential delta, which I will not tell you much about what it is, but it's a count of holomorphic sections of the fibration W bounded by capital L, asymptotic to ends in there. So maybe ignore this for now, but you should just know that what you get out of this is not L1 plus L2, but instead some extension of L2 by L1. Okay. So anyway, these functors can be defined. This one has been defined carefully. This one so far is mostly in people's minds. There's not a clean, careful geometric description of it. It's usually defined to be faster as going into modules and defined as the adjoint of that one, which is a valid way to define it, but it's a shame because there's actually nice geometry to be done here. So the question is, why do we care about this? And the basic answer is because this forms something called a spherical adjunction or a spherical functor. So I think this is something that was understood by people smarter than me, but maybe Abouzaid and Katzarkov, Sylvan, in different language, Nadler, probably others. Okay, so let's talk a bit about what's happening here. So all right. So these two functors I claim are adjoint to each other, but what's more interesting is that also there are exact sequences, exact triangles of functors acting on each of these categories separately that give you the cones of the adjunction and that have a geometric meaning. So there's in particular an exact triangles of functors on the Fukaya category of a fiber, which goes from the inverse monodromy to the identity functor to cap cup. So let's try to understand what this says. Well, what this says is, in fact, the logical conclusion of what you get when you think about the two pictures up there at the same time. Take a Lagrangian little l inside the fiber. Apply cup to it. So you move it around a U-shaped thing. Then restrict it again to the right, to the fiber. What do you get? You get the two ends of this thing, which are L itself and mu inverse of L. And gosh, my map is backwards. This is actually from L2 to L1, sorry. So what you get is indeed, this is saying that cup cap of L is isomorphic to a cone of something built out of the image of L and of monodromy, and L with a connecting map, which I will call S sub L, which is actually part of a natural transformation of functors from mu inverse to identity. And there's an exact triangle of functors going the other way around on the Fukaya category of y comma w, involving the opposite composition cup cap, which is telling you about a witness to the other adjunction. So why do we care about that? That's because we are getting to something that's very similar to a situation that's classical in algebraic geometry about inclusion and restriction functors. and specifically the instances of this that seem to come up in mirror symmetry, I'm thinking of inclusion and restriction when you have a divisor inside some ambient space. What is more interesting is that which is not clear. And so I'm going to show you, in fact, a pair of classes of examples that tell you that maybe you shouldn't be so assured about which one of these is the big space and which one of these is the small space. So yes? Yes, there are infinity functors. It's an infinity natural transformation, yes. Yes, everything in this talk is A infinity. And as is evident from that guy landing in twisted complexes, actually, I want to take triangulated enlargements. So mu is the monodromy of the fibration. Okay, so mu is the monodromy of the fibration W. Okay, so it's, you take a smooth fiber somewhere close to infinity, you move it all around a large circle, it comes back, it has moved in a certain way. What is S? S is a count of holomorphic sections. Actually, I can tell you, S sub L is exactly the count of, so maybe, let's move it this way. So take L here, take mu inverse of L, make this U-shaped thing, but bend it maybe even more forward or something. And then it's a count of holomorphic sections of W, of basically holomorphic disks with boundary in this fibered Lagrangian, whose projection is this kind of thing. And of course, the corner here will have to be an intersection between these two Lagrangians in the fiber, which is exactly how you get a morphism between them. And this is like the leading term of an infinity natural transformation. The next terms count similar things, but with more Lagrangians in the picture. Okay. So none of this is mine. This is like from Seidel. Okay. So before I go on to tell you, examples of this under mirror symmetry, let me plant another thought into your minds. The claim is, and this is at this point, this is like slightly on shakier ground, so maybe I should say in progress. All this also works if the fibers of W are themselves Landau-Ginzburg models. So by that I mean the fibers F carry some other function, maybe W sub F. And so on, if you wish. You can have as many levels of this as you want. Okay, so instead of just thinking of a Landau-Ginzburg model as being a family of symplectic manifolds, and then we can look at the family of their Fukaya categories and how it spreads over the base. And I think Michel Kapranov and his collaborators coined the term Schober for that and so on. I mean, anyway, this is like a locally constant sheaf of Fukaya categories over the complex plane with accidents happening at the critical values. Well, those Fukaya categories in the fibers, they don't have to be Fukaya categories just of the fibers. They could be themselves of the fibers with some functions. So the benefit of that is now you'll have a similar picture, but where for the fiber, you might actually have yes, and those functions, all the fibers carry a function, and I'm going to assume that at infinity, those functions commute with parallel transport. So there's a strong assumption. Basically, you need W and W sub F to Poisson commute at outside of a compact set. Yeah, sorry. So WF is in fact a function on Y restricted. Sorry, so yes, maybe I should say, okay, this is really the restriction to F of some function that I will also call W sub F on Y. Okay, and I want to imagine that its geometry at infinity doesn't change and is preserved by the monodromy of the main projection. So there's some strong compatibility assumption at infinity between these. No, that's right. And there definitely should not be any more for this to be interesting. But so we need basically parallel transport, if you want, between, well, maybe I should say just the monodromy of W. Of W to preserve the asymptotic, the stop of a fiber. By that I mean the subset where real part WF is very negative inside F. Otherwise, you can't really do that, right? Because your family of categories won't be, won't be well defined. Right? It will not come back to having the same. Anyway, okay. But that's a technical condition. You can ensure it. And so now when you have the same kind of statement, but with these extra data. And so I'm just adding the extra decorations to every functor happening in here. But surprisingly little has changed. Oop. Okay. Now there is one important question, which is, have you ever encountered one of these Fukaya categories with a space and two functions like that, and somehow some idea that one of them is the main one, the second one is a secondary one? Of course, probably that's kind of a rhetorical question in front of this audience. You guys don't think about this for a living. But in mirror symmetry, the answer is what usually comes up rather is situations where you have a space with a function which is a sum of terms. For example, in the mirror of CP2 that I had before, my function W was actually a sum of three terms. And those three terms corresponded to three different components of a toric anti-canonical divisor of P2. And the claim is whenever in mirror symmetry, you have a, let's say, normal crossings degeneration of a Calabi-Yau divisor, your Landau-Ginzburg models have these functions that want to split as sums. And the claim is a sum of functions or a pair of functions are essentially the same thing in this language. So the theorem in progress jointly with, let's see, what order? Ganatra, Jeffs, no, Hanlon first, and Jeffs, says under some independence assumptions, condition, the Fukaya category of Y, W, WF. So this thing that I've defined in two stages, things that are fibered for W and then within the fibers, nice for WF, is the same as the Fukaya category of W plus a small multiple of WF for Q much less than 1. Okay. So you should imagine that being well behaved for a sum of functions or being well behaved for both of the functions in practice, when the two functions are sufficiently independent of each other, are the same thing. So why is this important? Well, because this kind of connects different ways of doing toric mirror symmetry. When I drew this picture of CP2, I looked at the sum of three terms as a single projection, and I worked with that. Nobody has proved homological mirror symmetry for P2 that way since around 2006. Now, instead, people look at things that are simultaneously well-behaved for the three different projections given by the three different terms. And you get the same answer. And in this case, you can match by hand and check it works. But the basic reason is supposed to be essentially this, that you can trade being well-behaved for a sum of terms that are sufficiently independent or being well behaved for all of them separately. Yes, yeah, yes, it can be bigger than the dimension. In particular, for a toric Fano, you can have one term for each toric divisor, and this works. But then you have to be more careful about what you mean exactly. Because of course, the joint fiber of everything will be empty. Yeah. Okay. All right. So where was I going next? Yes, so sorry, I was supposed to give you, oh gosh, I'm almost out of time. Okay, so let me just tell you what this is good for in real life. So, but I did state at least some theorems. So the first kind of examples, there's two main classes of examples. The first one is if I have what I will call a log Fano. And so this is known really so far, to be honest, for toric things up to dimension 2 and a few other sporadic examples. This is not really proved in full generality. So log Fano means that I have a reduced effective divisor D with a property that some other divisor D prime is the anti-canonical class of X. So another way of saying it is D is part of a Calabi-Yau divisor on X. So once that's the case, what did I? That part of my notes. So the claim is that the mirror of X is something where the potential splits into a sum of two terms. Roughly speaking, those terms correspond to the deformation of the geometry of the complement of D union D prime, the log Calabi-Yau, obtained by partial compactification by adding D, or separately by adding D prime. And of course, you can add both, and that gives you all of X. And that's how the potential splits as a sum. So, all right. At the same time, we have also a mirror of D that comes for free, which is the fiber of W with the restriction of W prime. And so in that case, we can draw our functors. Oops, fiber. Okay. So we have two versions of homological mirror symmetry. One is for the ambient space X. This is going to correspond to dB of X. This one corresponds to dB of D. And in there, I have inclusion and restriction functors. And the statement is cup transporting over a U-shaped thing is mirror to inclusion push forward, while intersecting back with a fiber is mirror to the restriction. Okay. And these are indeed adjoint to each other on both sides, with the monodromy here corresponding to tensoring with O of minus D. If I didn't get my adjunctions backwards. So this is one class of examples. And in the last 0 minutes, I wanted to tell you about the other class of examples just to contrast them. So the other kind of example is joint work with Abouzaid. Let's say that you have any toric variety, not necessarily compact. And inside that, you have a smooth hypersurface, pretty much any hypersurface. And the claim is that we can produce mirrors using a construction that was known before, but we worked out in trying to work with Katzarkov, which produces a mirror to this situation. Sorry. So the mirror that we produce out of H is, in fact, something that's let's say this is of dimension n minus 1. This is a toric Calabi-Yau manifold with a potential that's the sum of two terms. So this one is kind of, the Calabi-Yau that you get is encoded directly and explicitly by the defining equation of a hypersurface, or rather a tropicalization of this equation. W0 is pretty much always the same thing. This is a single toric monomule. And then this one depends on what toric variety things live in. So the statement in that case is that we have, so the fiber, okay, because this is a toric monomule on a toric variety, the fiber of that is again a toric variety. And in fact, it's just C star to the n, always. So fiber F, which is C star to the n, with this W sub V, this is one of those toric Landau-Ginzburg models that are mirror to toric varieties. So this is known by toric mirror symmetry to correspond to the ambient variety V. And then we have cup and cap relating that to the other guy. And the claim is that these correspond now, cap corresponds to restriction and cap corresponds to inclusion. And the way, in fact, that this, so the main result we prove with Abouzaid is this equivalence, which is homological mirror symmetry for hypersurfaces, and building on that, complete intersections. The way we prove this is using this diagram, because this side was already well known. And so the main thing we have to understand is that there is this adjunction, that the monodromy of that corresponds to tensoring by the defining line bundle of H, and that the section counting, this natural transformation S, now is going to be given by a section of H, of O of H. And which one? Well, that's where one has to actually do calculations, stop doing algebra and do geometry and complex analysis. But the outcome is this natural transformation is exactly the defining equation of H. And therefore, you can push using this structure to get this equivalence here. So parting words, if you compare these two diagrams, it looks like one of them is backwards. Inclusion and restriction got switched around. The answer to that is basically an A-model version of derived Knorer periodicity. Orloff has this wonderful theorem that says if you have a hypersurface in something, maybe given as a fiber of a map to fit our setup, then what you can do is take the product of the ambient space with an extra affine line and equip it with an extra potential, which will be the product of a defining equation with a new coordinate. That produces something of complex dimension 2 more, which has the same B-model category. On the A-model side, the same is true, and that's basically the main thesis result of my student Gammage and Jeffs. So what's going on is there's a stage of somehow, I mean, this guy here, you can tell its dimension is too big, right? Because H has dimension n minus 1. This guy has dimension n plus 1. Well, we can't do better. Somehow, in general, Fukaya categories to be interesting enough, we might need a bigger space. But morally, that's not a problem because up to some kind of Knorer periodicity, this could have been some non-existent n minus 1 dimensional space. And then cap and cup inclusion restriction get kind of switched around under this. It's kind of a cool thing. Okay, thank you for your time.